So now we move to our last speaker of this session, and it is my real pleasure to introduce our last speaker, M. Raju, who also happens to be my batchmate or lab mate during my PhD. So M. Raju did his PhD from Thin Film Laboratory under the supervision of Professor D.K. Pandya and Professor Sujit Chaudhary. And during his PhD, he worked on understanding the ion beam control on the interface between cobalt iron boron and magnesium oxide. And he obtained his PhD in 2013. And then he briefly stayed at National Physical Laboratory, Delhi during 2014. And he worked on setting up a dilution refrigerator for millikelvin magnitude transport and developing ferromagnetic superconductor heterostructures. And then he moved to National Nanyang Technical University, Singapore, where he worked with Professor Christos Panagopoulos, where he developed a unique thin film multilayer system for room temperature nanoscale skyrmions and studied their Hall effect. And he's currently working with Professor Colin Broholm and Professor Satoru Nakatsuji at the Institute of Quantum Matter, Hopkins University, where he is developing a thin film fabrication facility for topological quantum materials. So with this brief introduction, I would like to invite our last speaker for his presentation. Yeah, over to you, Raju.
Can you hear me?
Yeah, just make it a full screen.
Okay, thank you so much for giving this time. And it's always a pleasure to come back and share my work with old friends and new friends. Let me briefly say, can you see my screen fully?
Yes, please go ahead, yeah.
Okay, I will be looking at specifically topological Hall effect emerging from skyrmions and multilayer samples. Multilayers made of heavy metals and ferromagnets, which some of our friends have been sharing in this workshop. I want to thank some of my colleagues who contributed directly to the work I'm sharing here. The top row is my colleagues at NTU. So we have basically thin film growth, transport, and room temperature MFM work going on. And each of us are basically involved specifically with different tools. And our colleagues at Technion, Israel, are experts in low temperature imaging. So most of all the low temperature MFM imaging I will be sharing comes from their work. And we have colleagues in Russia who try to look at topological Hall in disordered Skyrmion systems. And then colleagues at Max Planck tried to look at some band structure calculations, though we did not get too far, but they made an attempt. So just to point out, I think most of our friends already said, Skyrmions are basically nanoscale topological spin textures. They are characterized by a winding number, which comes from canting of the spins. Basically, they are 360 domain walls. In that sense, the way spin rotates, going from the center of the domain to the edge of the domain. So these textures are stabilized by competing magnetic interactions, basically aligning exchange interaction versus twisting DMI interaction. Depending on the system, how the DMI appears, one can stabilize a Neal kind of Skyrmion textures or block type Skyrmion textures. So Neal type, if you just look at across the Skyrmion, you are rotating the spin within the plane of the rotation. And if you look at the block Skyrmion, basically spin is going out of the plane as you go across the Skyrmion. That's the difference between Neal and block kind of Skyrmions. So as I said, it is stabilized. These textures are stabilized by competing magnetic interactions. In a conventional ferromagnet, you have aligning forces, which bring all the spins parallel to each other. But if you have a spin-orbit coupling, and inversion symmetry breaking, we have DMI interaction occurring, which tries to kind of twist the spins from each other. And in right conditions, one can really stabilize. One can really switch the spin direction between extreme center and the extreme by 90 degrees or 180 degrees, sorry. So such interaction can appear in interfacial systems like heavy metal and ferromagnet, the one I've shown here. And yeah, so to start with, these kind of topological spin textures initially were looked at or observed in B20 crystals where the M interaction is bulk kind. And another class of materials is interfacial DMI, which is basically thin film interfaces where heavy metal is placed on top or adjacent to a ferromagnet. So really room temperature skyrmions are kind of observed maybe about 8-9 years ago, and beyond that it's a heavy work. Again, within the interfacial systems, early works looked at basically low temperature work where skyrmions are stabilized at the interface between heavy metal and ferromagnet, but they never reached room temperature. However, it's, I think, Professor Ferd's and Vincent Cross group, which really looked at room temperature possibilities simply by stacking several interfaces of cobalt and platinum. For example, here we have two different heavy metals stacking cobalt in between them. And we just repeat such stacks several times, and such layers can stabilize skyrmions at room temperature. So going from low temperature to room temperature, basically, one has to stack several interfaces together. I think this is the, I would believe, early work, bringing room temperature skyrmions into play. And then there's a lot of studies towards that. So thinking of interaction that leads to skyrmion spin textures, a simple expression which deals with domain wall energy is helpful, especially domain wall energy in presence of DMI. What we have here is domain wall energy is lowered the moment you have DM interaction coming in, and basically at once the DMI interaction starts to dominate over exchange and anisotropy energies, you can basically make the domain wall energy negative, which means just proliferate these domains formation, and there are lots of them will appear. So there's a critical value for DMI, which kind of process one basically here. So this critical DMI is the value where you go from isolated skyrmion features to kind of dense arrangement of skyrmion features. And the ratio of DMI to the critical DMI is defined as thermodynamic stability parameter. In the coming slides, you'll see why this is so useful in understanding what is happening across these spin textures. So the material that I'm looking at is the combination of iridium, iron, cobalt, platinum, and we just stack them several times, in this case, 20 times. So as you can see, depending on iron to cobalt thickness, one can have large and isolated skyrmions or smaller, densely packed skyrmions. And this was not possible at that time if we are working with single cobalt layer. Instead, if we insert additional layer, we have kind of increased the control over DMI and anisotropy, which kind of helps to tune the skyrmion textures over a wide range, the size and density kind of parameters. Just to see if they are useful, one has to really work at controlling the nucleation size, speed in device configurations. That's when they are close to applications. But in this work, I will be just looking at characterizing these features in thin films through topological Hall effect. Just a brief kind of summary which captures different skyrmion materials tried in the literature and the range of size of those skyrmions. Again, simply looking at the size of skyrmions, one would be able to guess the kind of interactions dominant leading to that kind of skyrmions. For example, skyrmions of just few nanometers are kind of stabilized by spin-spin exchange or frustration kind of interactions, whereas skyrmions of 1 micron size are dipolar stabilized, and skyrmions about 100 nanometers are DMI kind of dominated materials. So this is kind of just an outline of different materials tried. So once we have the topic of my presentation is looking at topological Hall. Once you have an electron with a spin pointing up, as it crosses a skyrmion texture, the spin of the electron tracks the local moment of the skyrmion. As it tracks that moment, basically what is happening is electron does not move in a straight line. Instead, it crosses the skyrmion at an angle or deviates as it passes through the skyrmion. So that, in effect, is parallel to Hall effect, a normal Hall effect where a field applied deflects the charge carriers. But in this case, the field that the charge carrier or spin carrier is experiencing comes from uniquely from the winding of the skyrmion, which is distinct from the external applied field. In that sense, this signal comes from uniquely from skyrmion winding number or topological charge. This is an example of how we extract the signal. If you have normal metal semiconductor, one expects normal or ordinary Hall effect, which is proportional to field and charge carriers. If you have a ferromagnet or magnets, you expect additional component, which is proportional to magnetization and some scattering component. But if that ferromagnet stabilizes topological spin textures like skyrmions, you have additional component which is coming from the topological origin. So if you're measuring ferromagnets with skyrmions, you have all three components coming in. At the bottom, you have an example of how the total black curve is measured data, and the red curve is the modeled component of ordinary and anomalous Hall. And the difference of that is what we call topological Hall, which is uniquely skyrmion origin. This is an example of what we did. Basically, you have the total measured Hall signal here, and then fit that total Hall signal, assuming anomalous Hall component only after removing the ordinary Hall component. And finally, we arrive at the residual signal, which is subtraction of total and anomalous Hall components. Here, what I'm showing is actually, even when we are modeling anomalous Hall component, one can account for the longitudinal Hall resistivity as linear and quadratic components, or simply assume a proportional component, proportional constant, which is anomalous Hall constant. Whether you account for the specific shape of the longitudinal Hall resistivity or not, the residual signal does not really change. So yeah, we don't have to worry about the shape of the longitudinal resistivity in this kind of materials, at least. And when it comes to the magnitude of this topological Hall effect, it is proportional to the spin polarization, because that is the thing which is coupling to the magnetic moments of the skyrmion, and the charge carriers, which are reflected in the normal Hall coefficient, and skyrmion density, and the flux or the field associated with each skyrmion. So interesting thing about this is this skyrmion density, NSK here, captures the areal density of skyrmions. And that number can be arrived from two different experiments. One is simply, if you know the Hall, topological Hall magnitude, one can estimate the skyrmion density as skyrmion density coming from topological Hall as the ratio of these numbers. And independently, one can simply look at real space imaging, for example, MFM, and estimate this number and see how these two numbers correlate. Sorry. So there was a problem when people started looking at the topological Hall effect in this kind of multilayers and in different kind of materials, going from all metallic to oxides and ferroelectric materials. In all these interfacial systems, what people have seen is Skyrmion density estimated from transport seems to be very large compared to imaging image Skyrmion density. So the problem was to explain where that large discrepancy of several orders of magnitude comes from. One observation is that when we are simply looking at different materials like this, we know that all these materials are looking at skyrmions which are stabilized under different conditions. For example, temperature, field, or thermodynamic stability parameter. So, and each paper discussed that there seems to be large signal captured in the transport compared to imaging, and there was not real explanation or identified what are the parameters controlling this. So what we have done, but this is not, that was the problem with the multilayer skyrmions, but that's not the case for B20 bulk single crystal skyrmions. For example, here what I'm showing you is B20 single crystals where like materials like iron germanium or manganese silicon, where skyrmions form as a proper clear lattices. There, if you estimate the skyrmion density coming from the transport versus skyrmion density coming from imaging, they are more or less very close. There's no few orders of magnitude difference. So the discrepancy seems to come in the interfacial systems, not so much in the bulk systems. So what we have done was to kind of manage to control the skyrmion properties in a single material. Sorry, I want to. Single material where we are continuously tuning the skyrmion properties by changing temperature, field, and thermodynamic stability parameter. And the quantity of interest is simply tracking the skyrmion density coming from transport versus imaging and look at it as a ratio of these two parameters. So the combination of transport and imaging gives a complementary tool to understand what is going on in interfacial skyrmion systems. So this is an example of a specific composition of iron 0.4 angstroms to cobalt 4 angstroms. And what I'm showing you here is field evolution of skyrmions and track the topological Hall signal. As you go from low field to a high field and beyond saturation point, you can see in the MF imaging at intermediate fields, there is a dense arrangement of skyrmions, and the skyrmion density decreases and eventually disappears once we go beyond the saturation field. What is interesting in the Hall signal is that as a function of field, topological Hall signal distinctly kind of captures two peaks as you sweep the field. And the peak with smaller magnitude happens to appear for dense arrangements. On the other hand, peak with a larger magnitude appears for the less dense skyrmions, which is non-intuitive. I mean, which is in contrast to what people assumed, that skyrmion density increases topological Hall signal. That is true, but in this case, we need to understand what is happening between dense arrangements versus isolated features. So that's the focus we first put in to understand why less dense skyrmions appear to produce larger signal compared to dense arrangements. So one can control the isolated skyrmions versus dense arrangements simply by choosing composition of the layer or sweeping the field in a given fixed composition. So depending on what is the composition, one can only stabilize isolated features or stabilize dense features and then play with them by applying field around that features. So what happens is consistently, whenever we have isolated skyrmions, there's a larger magnitude of the Hall signal compared to dense arrangements. And now we look at the ratio of density of the skyrmions captured as the transport versus imaging. What happens is, as we tune the skyrmion density, the discrepancy, which is the ratio of transport image skyrmions decreases in a systematic manner. And once we are like very densely packed skyrmions beyond 100 or so per micrometer square, the ratio approaches close to 1, which is the case for B20 skyrmion lattices. So the observation that the large discrepancy is coming in the interfacial systems seems to be very focused in the isolated regime, not so much in the dense skyrmion regime. So what is happening as we go from dense arrangements to isolated features? Simply by analyzing the features for their configuration, we know that going from isolated to dense arrangement, there is a disordered lattice forming in the dense arrangement case, which points to the phase transition of involved across this change of configurations. So in our analysis, we see that once the skyrmion density goes beyond 20 per micrometer square, slowly the nearest neighbor coordination number approaches 6, and the angular orientation of those neighbors kind of converges to 60, which is the case for hexagon arrangement of skyrmion features. So this kind of transition is said to be indeed second order phase transition, and the question is, how does that affect the topological Hall magnitude in these systems? So to answer that question, first we had to kind of establish some kind of phase diagram which captures the transition from isolated to dense arrangement of skyrmions over a wide range of temperature and magnetic interactions. So what we have done here is, by simply playing with iron to cobalt thicknesses, we created a semi-phase diagram where we sweep the temperature for each composition and then generate this temperature versus magnetic interaction strengths phase diagram. So here, this blue shaded region captures the area where we go from isolated features to dense arrangement. So as you see, as the temperature is dropping, we need larger thermodynamic stability to push from isolated to skyrmion lattice. So now, once we establish this boundary, we wanted to look at what happens with the topological Hall signal as we go from across this phase diagram. So this is the phase diagram I just showed, and we just tracked the topological Hall signal across this phase diagram as a function of temperature in the bottom panels, and as a function of, at a fixed temperature, as a function of thermodynamic stability parameter. As you can see, topological Hall signal creates a local maximum as we go from isolated to skyrmion lattice in this phase diagram. Either you are looking vertically or horizontally. That is the case. So what is the mechanism that is driving the enhancement of topological Hall signal at this boundary? Again, when I say boundary, this is not very sharp given the disordered or imperfect nature of the interfaces of these samples. So here, what I'm just showing is kind of schematic of phase boundary, how it changes as a function of temperature versus thermodynamic stability parameter. What happens is, if you're sitting right around thermodynamic stability parameter 1, which is the transition point for stabilizing dense arrangement of skyrmions, one can actually simply by varying temperature or taking, there exists a critical temperature and critical thermodynamic stability parameter. And simply by traveling across this boundary, one should be able to kind of track what is the critical parameters for moving from isolated to skyrmion lattice. So as I said, to travel across this boundary, one had to simply define an effective temperature, which is product of temperature versus product of temperature and thermodynamic stability parameter. Again, the thermodynamic stability parameter here is a dimensionless quantity, so their product still contains the units of temperature, which is some sort of energy. So what we define here is that if you're working right around the transition the product, the effective temperature T prime, also captures the critical property of Tc as we want to study the transition point. So if you fix your if you're going in this phase diagram either horizontally or vertically, you can look at the transition point. What we are looking at here, because of the convolution of these parameters, we cannot really experimentally fix one and change the other. Both of them are changing simultaneously. So to capture that, we define effective temperature as a product of these two. And once we have such modified or effective temperature and plot the topological Hall ratio between transport and imaging, and as a function of the effective temperature, what we see is divergence of that Hall signal around like around 100 Kelvin. This divergence of the Hall signal across the transition point is consistent with what is expected for a second order transition where power law kind of behaviors emerge. So this red curve here is indeed a power law fit to this data set. Though we wish to have many data points on this, but the data we have already seem to suggest indeed there's a power law behavior. So here we go a little further to kind of analyze what is happening. What can we extract from that power law behavior? If we were to simply think of Landau second order phase transition and identify an order parameter and analyze this behavior in terms of fluctuations at the phase boundary, spin fluctuations at the phase boundary, and ordered phase emerging after the transition. So these two temperature or critical temperature dependent behaviors or power law behaviors can indeed explain this behavior, and one can extract the exponents leading to identifying what universality class of phase transition is involved in this case. I haven't really put the details of fluctuation analysis here. You might look at our paper for that. After this analysis, once we look at the log-log plot of this power law behavior, we arrive at beta of 0.31, gamma of 1.88, which points to some kind of 3D Heisenberg spin system where the exponents are modified by 2D character of the layers. So to summarize, what we have seen is a phase boundary, a critical fluctuation of the phase boundary influencing the topological Hall, and a power law behavior emerging at the boundary. We can have three different kind of approaches. If you're just simply looking at MFM, we identify the boundary by analyzing MFM images, and by looking at where the topological Hall diverges with respect to imaged Skyrmion density, we identify another region in temperature versus kappa space diagram, which seems to overlap with just imaging data. And finally, when one can just look at purely transport and see where the topological Hall generates local maximum. And that's this curve. You can see that approaching this problem from different experimental tools, we can identify a temperature and kappa regime where one can have enhanced topological Hall. So to summarize, in the interfacial systems, there is basically chiral fluctuations increasing the topological Hall. And most of the literature is actually focused in the isolated Skyrmion regime and reporting different kind of topological Hall magnitude. If they were to push in the extreme right, once there's lattice formation, system would approach a B20 single crystals. Yeah, that's all. Thank you for your attention. Let me know if you have any questions.
Yeah, thank you, Raju, for this very nice talk. And so I think we will have some questions. So anyone? Yeah. So Professor Mudli has some questions to ask to you. Yeah, please go ahead.
Raju, very good talk. I really liked it.
Thank you.
So I was wondering, what is this effective temperature that you talk about? What is it due to the fluctuations or?
Usually, if we are studying a unique or ideal system, one would have a critical parameter which defines the transition. But for multi-layer systems, we don't have enough systems where one can really standardize and identify this. So we are trying to identify critical parameter which drives the phase transition between isolated and dense Skyrmion configurations, and identify that critical point which links to phase transition phenomena, critical phenomena, that critical point where topological Hall diverges. Yeah, I'm not sure if I answer your question.
Yeah, it's because of the multi-layer you have a different effective parameter. Okay.
Yeah. Do we have?
Okay. Thank you.
Do we have more questions?
Yeah, hello.
Yes.
Sir, so some question regarding the first session. So I want to ask some question from Himanshu sir regarding oscillator.
Yeah, but yeah, you can ask this later. But I mean, let's focus on this particular presentation. Do we have some questions? Yeah, you can ask
Yes.
later. But yeah.
No, sir.
Raj
I
has
have
some
some question for Raju, sir.
Yes, Sajid, yeah, please go ahead.
Yeah, thank you. It's always excellent talk from Raju, sir. I always enjoy your talk. Thank you. Thank you very much. So,
thank you, Sajid.
was for imaging, you basically image from the top using MFM.
Yeah.
But you know, the structure is multi-layer, and
Yes.
its thickness is huge. So in transport measurement, you basically probe throughout your structure. So do you
Yes.
think that the Skyrmions are even more vertically when you transport when you do transport? Or I was wondering about that. So maybe you can answer.
To answer your question, I think we need to look at imaging which is in transmission mode, for example, MTXM or Lorentz TEM. At least one experiment we did was to look at MTXM at both iron edge and cobalt edge. What we found was both iron edge and cobalt edge seems to produce similar kind of Skyrmion densities in the transmission experiments. So we assume that Skyrmions, what we see in the MFM, are indeed representative of the structure throughout the multilayer. And we also try to track the Skyrmion density in the MFM versus Skyrmion density in the MTXM. So one is surface technique, one is transmission technique. And look at the Skyrmion density as a function of field. They reasonably overlap, which suggests the density of Skyrmions that we are getting in the MFM image is somewhat true representative of what is happening across the layers.
Okay, perfect. So the Skyrmion is quite elongated. It's not like a sphere Skyrmion. It's basically
I mean,
a vertical, cylindrical Skyrmion.
there could be Skyrmions coupled throughout the multi-layers.
Okay.
Yeah. Because of the
Thank you.
exchange interaction, they are aligned with each other. That's what I would think.
Okay, thank you.
So we have two more questions. So yeah, please, Vincent Cross wants to ask something. Yeah, please go ahead.
Yeah, hello. Thank you very much. Very nice, interesting talk. I have a question. In fact, as far as I know, nobody have seen such divergence of the topological Hall contribution in B20 materials, so in bulk like DMI materials. And the question is why? Can you comment on this?
In B20 compounds, unless you do some good thermal control, we will not be able to stabilize metastable Skyrmions. So the enhanced Hall signal, topological Hall signal, seems to be characteristic of isolated Skyrmions. So in case of B20 compounds, if we quench the sample from high temperature, we will be able to stabilize metastable skyrmions. There, immediately once the lattice goes into metastable state, you see topological Hall magnitude going up even in B20 compounds. So it seems to be spin fluctuations around isolated phase that are contributing to this enhanced. There is a paper which talks about enhanced topological Hall in the metastable phase of B20 compounds.
Okay.
Yeah.
I don't know. I will check that. Thank you very much.
Probably I can send you the paper and reference.
Will be good. Thank you. Thank you in advance.
Thank you. Yes.
Yeah, one more question from Brindavan Oja. Yeah, please, Brindavan, go ahead.
Yes, I have one question regarding measurement technique related. So when you are measuring the topological Hall effect, so are you preparing any Hallbar kind of device? Or
as I said, we are just looking at thin film. We also measure the Hallbar and compare the magnitude. And once we have stronger anisotropic samples, we seem to have Hallbar seem to behave differently from the large size film. And when we are subtracting the anomalous Hall based on the magnetization measured in the squid, for example, so it's very difficult. So what we did was to just stick to large size thin film, where we are confident that magnetization is not changing. I think that is crucial. So magnetization is kept constant between sample measured, the transport sample versus sample measured in the squid.
okay, means I mean you have measured in the samples in Van der Waals geometry in
no, it's a rectangular geometry. Yeah.
Okay, I understood. Okay, thank you.
There is one participant, PD. I don't know what's the name. Yeah.
So, sorry, somehow I think this was. So I'm Pintu Das from.
Okay. Good to see you. Yeah.
Yeah, nice. Very nice talk actually. Enjoyed thoroughly. So just one point where I stumbled upon. So are you saying that the topological Hall effect that that is reported is due to the isolated skyrmions mostly? That is what you were saying?
Yes. Most of the multilayers in the literature are actually in this regime. I don't think anyone has pushed deep into the lattice regime yet.
But
in our case, that was
right. But this Hall effect, this topological Hall effect, is proportional to the skyrmion density, right? So if you're in the isolated regime, you should definitely see this other effect on the lattice regime, right? And which should be stronger. So what is your comment on that?
So what we should expect is, if you are working just with the lattice skyrmions or just with the isolated skyrmions, there should be a linear dependence on skyrmion density. If I sit in the isolated regime, simply track topological Hall as a function of skyrmion density, we should have a linear behavior. If I sit in the skyrmion lattice regime and track the Hall signal, it should be linear with skyrmion density. So that linear relationship is still true as long as we are strictly in one phase, not going across the phase. So we did track Hall signal as a function of skyrmion density in the isolated regime. I haven't put the data here, but it's in one of our papers.
I see. So we have actually performed some Hall effect measurements. Actually, this my student Humul Saran has shown some of this data, and there we see very clearly actually two different features in the Hall effect, in the topological Hall effect.
I was looking at that, and I think I understand a little bit on what is going on. Actually, we also tried to track the relative magnitude of this first peak versus second peak. And if we are sitting at the transition of out of plane to in plane transition, anisotropy transition, at some point, the magnitude of the first peak goes up compared to magnitude of the second peak. I don't have that data here, but I think that is what is happening in your samples.
But in our case, so what we see is the stronger peak actually matches with the lattice. I think the larger density. So that's what we are seeing in our experiment.
Yes.
So maybe
yeah.
So maybe we can discuss that later. So,
yeah, sure. Yeah.
Thank you very much. Thank you.
Yeah. Welcome.
Yeah, so Raju, I have one very general question. So because since you have worked a lot on this area, so where are we going ahead with this lots of studies on this Skyrmion? We have Skyrmion, anti-Skyrmion, and all these things. So what's your take on it?
I think the whole idea of Skyrmion, pursuit of Skyrmions was we will have, I mean, there are different directions, but at least it was racetrack kind of memories. And the Skyrmions were supposed to move at ultra low current densities. That is what is observed in B20 compounds. This current critical current density there was about 10 power 6 or to 10 power 8 amperes per centimeter square. But what we see in these materials, in multilayer materials, the critical current density for moving these features is about 10 power 10 or 10 power 11 and 12. And they do not move. The maximum speed I have seen is like 100 meters per second in some of these multilayers. That is way below what domain wall is capable of for the same current density. So in terms of racetrack kind of applications, it's not moving as fast as domain wall, maybe because of the pinning in this disordered multilayer kind of systems. Yeah, I think that is the critical thing to fix. Once we have better speeds, and then if one is able to work with synthetic antiferromagnets, I think that is a way to go to make them useful. And the other thing is to really find ways to stabilize these in the antiferromagnetic materials and find ways to image them. It's very difficult because there's no stray field or no net magnetic moment, so it's hard to image them. But ferromagnets is another good direction because there you have sublattice unequal magnetic moments, which still seem to allow imaging. Yeah, I think that's what I think. But then more exotic directions are people look at coupling these features with superconducting vortices and trying to see what could be done in terms of quantum information, things like that. Yeah.
Thank you. So I think we don't have more questions. I think